Now I would like to explain about the transient response of RL series circuit with sinusoidal excitation by using Laplace transform method. Okay, last class we discussed the transient response of RLC circuit with sinusoidal excitation with the differential equation method. So next same topic with Laplace transform method. So consider a series RLC circuit as shown in figure. Okay, this is series RLC circuit. Here resistor, inductor, capacitor connected in series connection, and input voltage is sinusoidal voltage V equals to Vm sin omega t, and here circuit current equals to I of t. So let 0 initial conditions. So it means initial inductor current value equals to 0, initial capacitor voltage value equals to 0. Here switch is closed at t equals to 0. Here arrow direction downward direction, it indicates the switch closed at t equals to 0. So now we have to find the I of t expression from t equals to 0 plus to infinity. So circuit total time t equals to minus infinity to plus infinity. Here switch operates at t equals to 0. So from t equals to minus infinity to t equals to 0 minus, switch position open position. So supply not connected to circuit. So next from t equals to 0 plus to t equals to infinity, switch position closed position, supply connected to circuit. So now we have to find the I of t expression from t equals to 0 plus to infinity. So draw the circuit from t equals to 0 plus to infinity. So 0 plus to infinity, switch position closed position, here short circuit. So now apply KVL. So KVL equation I of t into R plus L into di by dt plus voltage across the capacitor 1 by c integral I of t into dt equals to V. Here V equals to Vm sin omega t. So first one voltage across the resistor. So formula V equals to IR. Here current equals to I of t, resistance value equals to R, I of t into R. Next inductor voltage equals to formula L into di by dt. So L into d by dt of I of t. So next voltage across the capacitor 1 by c integral I of t into dt equals to input voltage. Here input voltage equals to Vm sin omega t, sinusoidal voltage or AC voltage. So now by applying Laplace transform. So Laplace transform of I of t equals to I of s. Laplace transform of d by dt equals to s into I of s minus I of 0. Okay, Laplace transform of d by dt of I of t equals to s into I of s minus I of 0. Next Laplace transform of integration equals to 1 by s. So 1 by s into I of s plus initial charge value or initial voltage value. So by applying Laplace transform to this equation, we can write I of s into R plus L into s into I of s minus I of 0. This is initial current. So plus 1 by Cs I of s plus Q of 0 by Cs. Okay, equals to Vm into Laplace transform of sin omega t equals to omega by s square plus omega square. Okay, this is initial voltage value, capacitor initial voltage value, and it is inductor initial current value. So here initial voltage value, initial current value equals to 0. So why? Because here switch operates at t equals to 0. So assumption initial voltage across the capacitor equals to, or initial current in inductor equals to 0. So inductor current value, capacitor voltage value at t equals to 0 plus equals to 0. So these two values equals to 0. So this equation becomes I of s into R plus L into S plus 1 by Cs equals to Vm into omega by s square plus omega square, or I of s equals to Vm into omega by s square plus omega square into R plus L into S plus 1 by Cs, or it equals to Vm into omega s by L into, by taking L common, L into s square plus omega square into s square plus R by L into S plus 1 by LC. Okay, we can write this equation like this. So next it equals to Vm into omega s divided by L into s plus j omega into s minus j omega, s minus alpha into s minus beta. So assume here the roots of this quadratic equation equals to alpha comma beta. So we can write this equation equals to s minus alpha into s minus beta, and here these roots are j omega. So it can be written as s plus j omega into s minus j omega. Okay, this is the next equation. So here alpha and beta are the roots of this equation. So by using formula minus b plus or minus square root of b square minus 4ac, we can find this equation roots. So here alpha equals to minus r by 2l plus square root of r by 2l whole square minus 1 by LC, and beta equals to minus r by 2l minus square root of r by 2l whole square minus 1 by LC. So by using formula minus b plus or minus square root of b square minus 4ac by 2a, so we can find these two values alpha comma beta, these two equations alpha comma beta roots. So I of s equals to k1 by s plus j omega, k2 by s minus j omega, k3 by s minus alpha, k4 by s minus beta. So by applying partial fraction, we can write this equation like this. Here k1 and k2 and k3 and k4 are constants. So by using partial fraction method, we can find these constant values. So next, by applying inverse Laplace transform, we can write I of t expression. So I of t equals to k1 into e power minus j omega t. So L inverse of 1 by s plus e equals to e power minus et. So here s plus j omega, 1 by s plus j omega, inverse Laplace transform e power minus j omega t plus k2 into e power j omega t plus k3 into e power alpha t plus k4 into e power beta t. So in steady state condition, with the steady state current equals to, so Vm by root of r square plus 1 by omega c minus omega L whole square sin omega t plus pi plus theta, and theta equals to tan inverse of 1 by omega c minus omega L by r. Okay, in problems, by using the values of RLC, we can find these values k1, k2, k3, k4, and finally I of t expression. Okay, like this. So next one here, the roots of the characteristic equation. If r by 2l whole square greater than 1 by LC, the roots are real and different. In that case, the response is overdamped response. If the r by 2l whole square less than 1 by LC, so the roots are imaginary, the response is underdamped response. If r by 2l whole square equals to 1 by LC, the roots are real and equal. In that case, the response is called critically damped response. Here the characteristic equations, roots are alpha comma beta. So based on these two values, alpha comma beta values changes if r by 2l whole square greater than 1 by LC. So in that case, roots are real and different. So the response is called overdamped response. If r by 2l whole square less than 1 by LC, the roots are complex conjugate. In that case, the response is called underdamped response. If r by 2l whole square equals to 1 by LC, these two values become 0. So alpha equals to minus r by 2l, beta equals to minus r by 2l. In that case, the roots are real and equal. So the response is called critically damped response. Okay, here k1, k2, k3, k4 are constants. So by using partial fraction method, we have to find these constant values, and if we substitute, finally we get this expression. Okay, final the current expression. So next, based on the r by 2l and 1 by LC values, the response changes. First case, the response is called overdamped response. Second case, response underdamped response. Third case, response critically damped response. Okay, here this is the given circuit. Here switch closed at t equals to 0. So first we have to write the KVL equation. So next, by applying Laplace transform, we can convert this function of t equation into S domain. Okay, this is S domain equation. So next, by applying partial fraction, so we can write this equation like this. So next, find constant values. Next, by applying inverse Laplace transform, so finally we get the current expression I of t. So based on the alpha comma beta values, the response changes. Okay, in different cases, different responses are present. Okay, that response depends RLC values. So resistance value, inductance value, capacitance values decides the type of response of the network.